Hi, I'm Alistair, and this video is inspired by an advert that appeared in my Facebook feed recently. And this was an advert for a product called Smart Dice. So these were dice that have electronics in them, and they connect to a mobile phone app. And what happens is you roll the dice, and then the app displays the total of the value of the dice that you rolled. And this seemed to me sort of a perfect example of a solution to a problem that doesn't really exist. I've never really had an issue in rolling a set of dice and then just looking at the value of the faces that were pointing upwards rather than needing an app to add them up for me. But it did make me think about the technology involved, and I wondered whether I could use that in an escape room puzzle instead. Now, you wouldn't want to use regular sized dice in an escape room because they're small and they go missing, so I kind of made this jumbo dice instead. And hopefully what you've been able to see is if I rotate the dice like this, the image on the screen behind me shows the value of the topmost face. And you can imagine this being the basis of an escape room puzzle where players have to turn the faces to make a numeric sequence, for example, in the correct order. Or maybe you've got several of these dice in the room. Let's say that you've got an escape room based around the story of a famous gambler, and he lost lots of money in a craps game, let's say. So what players have to do is to arrange a set of dice to mirror the value of the final roll that he made. Or these don't have to be dice at all. Here I've got another cube which you might recognise from another context. And let's say this was the basis of a cipher puzzle instead. So you've got some arbitrary symbols on the cube here. And what players have to do is rotate the cube so that a given symbol is pointing upwards. And when they do so, they get displayed the meaning of that symbol on a screen somewhere. They can then use that as the basis to translate a code that's written somewhere else in the room. So there's lots and lots of different ways you could use these kind of puzzles, and they're pretty straightforward to build. So each one of these cubes contains an ESP chip. That's very similar to an Arduino, it just has a built-in Wi-Fi as well. They've also got a linear accelerometer. That's the thing which actually detects which way up the cube is pointing. And that's similar to you'd get in a mobile phone, for example, to detect whether you're pointing in portrait or landscape mode. And what happens is the ESP polls the sensor, it works out which way the cube is pointing, and then it sends that as an MQTT message to a Node-RED instance that's running on the computer behind me, and that's what updates the display. They're very cheap and pretty straightforward to build. They only cost about $5 each in components for each one of these. And in the rest of this video, I will show you all of the hardware and the software you'll need to be able to make one yourself. So to talk you through the hardware in a bit more detail, let me just pop open one of these boxes so you can see what's inside. So here we go, and you can see at the bottom here I've got a LiPo battery. This is a 3.7 volt battery. That is plugged into a Wemos D1 Mini through this little battery shield on the top here. And then on the right hand side, this is the accelerometer that we're going to use. So if I zoom in a little bit more on this sensor, this is a GY521 board. And in fact, it not only has an accelerometer, it has a gyro and it also has a thermometer sensor in it as well. But the part of it we're going to use is just the accelerometer. Now, you might find that surprising because you might think, well, an accelerometer, surely that is for detecting forces that are acting on the box. So if we were to jiggle it left and right or something like that, surely that's what an accelerometer detects. But you'd be wrong, because those are external forces, but in fact we've constantly got the force of gravity acting on the sensor itself. So normally we're looking at the top down, so gravity is acting straight through the chip in its Z axis. But if I show you it again, actually look at the markings on the board here, you see a little X arrow here pointing to the right, and we've got a Y arrow here pointing upwards. So these are the other axes that the accelerometer recognises. If we have the box on this side, Obviously the force of gravity is still pointing in the same direction, which is straight down, but now it's acting through the x-axis of the chip. And if we have the cube this way up instead, now it's acting through the y-axis of the chip. So even though we don't have any external forces jiggling the box around like that, the accelerometer will still be used to detect which way the box is up by these axes as marked here, and working out which one of those axes is experiencing the constant acceleration due to gravity. Now the sensor itself is connected to the Wemos board here through an I2C connection. You can't see that very easily because I've mounted them on this proto board here. And the reason for that is to make sure that the box is robust enough, so if we wiggle it around or if the players turn the box upside down, it sort of doesn't come loose at all and the connections are secure. If I show you one of the other boxes, this was sort of an earlier prototype, so I haven't done it quite so neatly. And here you can see the yellow and blue cables here. These are the data and the clock lines which I'm using to connect the Wemos here to the sensor board. And in fact, if I show the other cube as well, this has a slightly different variation because here I've also got cables as well going to the sensor, but now they're wired to an ESP32 board instead. So in fact, you can use any processor really with this setup at all. You could use an Arduino Nano if you wanted to. That wouldn't have a built-in wireless connection as the ESP chips do. But if you wanted to have something contained within the board that was completely local, that would work perfectly well. The reason why I'm favouring the Wemos board particularly is because it comes with this battery shield here, and that means you can keep the LiPo battery connected to it, and it can charge through this USB port here. Obviously, when you've got any portable props, you need to give consideration to how you're actually going to power them and keep them charged. And this is a really convenient little shield that enables you to do that. So it's a bit hard to see the wiring inside those little boxes. So let me show you a diagram in Fritzing instead. So here we've got our sensor board, and it's got the linear accelerometer chip in the centre of it there. Then we've got our Wemos D1 Mini, which has the ESP8266 chip. That's what we're using as the processor in this project. And then we've got a LiPo battery that's plugged into this battery shield here. Now, as you can see, the wiring is pretty straightforward, but there's a few points I want to mention, particularly concerning power and voltage levels. So let's start by looking at how we supply power to the Wemos board itself. So this is a portable project, which means it needs to be battery powered, and I'm using a single LiPo battery. So this is a rechargeable battery that provides a high current output, and that means it's well suited for powering these kind of projects. They typically output 3.7 volts, as you can see indicated on the battery there, but on a fresh charge it could be anything up to about 4.1 volts. Now, on an Arduino, you might be aware that it has a V-in pin, and that V-in pin goes to a voltage regulator, which means that you can supply a DC power supply of anything between about 7 volts and 12 volts, and it will be stepped down to an appropriate voltage for the board itself. So on an Arduino Uno, you've actually got a little DC barrel jack you can use. On an Arduino Nano, you've got a V-in pin, and those accept quite a wide range of voltages. Now, on the D1 Mini, however, you don't have that. What you've got is you've got a 3.3 volt pin, you've got a 5 volt pin, and you've got a USB port at the bottom, which needs to have exactly 5 volts as well. And if you supplied any greater voltage power source to any of those pins, you'd end up frying the board pretty quickly. So that's one of the reasons why this battery shield is great. This lets you plug in a 3.7 volt input from the battery, and it's got these components on board which will step up that supply to power the 5 volt line, and it will also regulate the power down to 3.3 volts, and it simply slots on top of your Wemos board like this, completely seamlessly, so it doesn't affect any of the pin output like that. And as I mentioned before, you can leave the battery plugged into this port here and recharge it through the board itself by simply connecting to this USB socket here. So that's a really nice way of powering portable projects. Now, in two of the cubes I demonstrated in the video, I didn't actually use the battery shield at all. Instead, what I did was I took the output from the battery and connected it directly to the 5 volt and to the ground lines on the Wemos. And although this might not be considered best practice as such, it will work absolutely fine. So to try to explain why, remember that I said all of the components on the Wemos board actually run at 3.3 volts, and it has a regulator on board which steps down the 5 volt power supply. So if we'd plug this into 5 volts, or if we'd got a USB cable connected here which also supplies 5 volts, these pins go through that regulator and step it down to the safe 3.3 volts, which is going to provide everything on this board. We've plugged in a 3.7 volt power supply, and that's above 3.3 volts, so it will get stepped down in just the same way that a 5 volt power supply would be. Now, the only difference is that it is not going to get stepped up at all to 5 volts. So if we had any other components over here, let's say, that we were looking to power from that 5 volt line here, they would not receive the 5 volts they were expecting. They would only get the 3.7 volts that we are initially supplying on that pin. Now, that's not going to do any damage to any board. The worst it's going to do is perhaps not power them up correctly. But for the component that we're actually using in this case here, this only wants 3.3 volts anyway. So we're supplying it to the 5 volt line, which has actually only got 3.7 volts on it. But the first thing that's going to happen is it will be stepped down to 3.3 volts anyway. You obviously also lose the convenience that we had with the battery shield of being able to recharge the battery without doing any further modifications. But otherwise, this will actually work just fine connecting the 3.7 volt supply to the 5 volt. What you must not do, however, is to supply the LiPo battery directly to the 3.3 volt pin. If you were to do this, we are supplying a greater voltage to that pin. This is not going to be regulated any further. This is connected directly to a lot of sensitive components here which really do not want to exceed 3.3 volts, and that will cause some damage to your board. So don't do that. But it is perfectly safe to do that, and in situations like this that are relatively straightforward, that will actually work just fine. Okay, now let's look at the interface between the Wemos and the sensor board itself. So the ESP chip on the Wemos runs at 3.3 volt logic. So when you write a high signal to any of the GPIO pins, they carry 3.3 volts. And the sensor board over here also runs at 3.3 volt logic, so this is perfect. What that means is that we can connect the system clock line of the I2C interface directly to pin D1, and we can take the data line directly from SDA to pin D2, and we don't need to worry about any kind of logic level converters on those signal lines or anything like that. These will just carry signals at 3.3 volts between the boards. And then we supply a ground line, and we also supply a VCC line. Now I've connected this to 5 volts rather than 3.3 volts. The sensor board here, although I said it runs at 3.3 volts, it actually has its own voltage regulator on board as well. So you can supply it with a 5 volt power supply, that's fine. It will step it down to 3.3 volts here. I could instead have powered it from 3.3 volts on this side. There's really not much difference. This would simply be using the regulator on the board here instead of the regulator on the board here. Either way, it ends up being at 3.3 volts, and this is all the wiring that you need. Great. Now, I did mention in the video earlier that you could use an Arduino board instead. You don't get the Wi-Fi interface that you get on a Wemos, but let's say that you want to have a completely self-contained box. Maybe it has a lock that pops open when it's rotated in the right direction, so you don't need that external interface. Now if that's the case, you can wire it almost exactly the same way. Now if you've been paying attention, you might find that a little bit surprising, because you think, well, hang on a minute, an Arduino runs at 5 volts. So okay, I've got my ground and I've got my 5 volts going to VCC, which I've told you is going to be stepped down to 3.3 volts here. But surely the clock and the data lines here, well, the Arduino is writing a 5 volt high signal here. Isn't this going to be too much for the sensor board to handle? And the reason that that's okay is that I2C is what's called an open drain interface. So what that means is that the Arduino never actually writes a high signal to these pins when it wants to send data. What it says instead is it pulls those pins low to ground. So the two states of a wire in an I2C board are either floating or they are pulled low. Okay, great. Now if you're really paying attention, you might think, well, hang on a minute, that's still not right though, because when the Arduino is not writing to them, they must be being pulled up to a known state. And if this is a 5 volt Arduino, surely the known state is going to be 5 volts. And you'd be right there as well. But here's the thing. On an Arduino, when you use the I2C wire library, when you're not writing a signal, what happens is that these two pins here are initialized using the onboard pull-up resistors, which are pulled up to 5 volts. But the pull-up resistors on an Arduino are very weak. What that means is they're actually quite high resistance value. They're around 50 kiloohms. Now if we look at the datasheet for the GY3F21 board, the sensor board we're using, they pull up the signals, the data and the clock lines, to 3.3 volts, but through a much lower value resistor. These are only 2.2 kiloohms. So because the resistors used on the 3.3 volt sides are so much lower value, they're the ones that are going to have the greater significance, the greater influence over the voltage that those lines are pulled up to. And in fact what you'll find is that the value, the voltage, when these lines are left open, is perfectly within the tolerance level of the sensor board. So even though the Arduino is theoretically pulling them up to 5 volts, because those onboard resistors are so weak, they actually have negligible effect, and we can let the sensor board pull the I2C data lines up to 3.3 volts instead, and they're absolutely fine. So that was a bit complicated. I hope that made sense, and I sort of did a job of explaining that. But what it basically means is either way, if you are using a 5 volt device like an Arduino Nano, or if you're using a 3.3 volt device like a Wemos D1, or if you're using an ESP32 as well, you can simply connect VCC to either 5 volts or 3.3 volts, because it will be stepped down on the board anyway. You connect ground, and then you connect the clock and the data lines to the pins that are assigned to those roles on your board. On a Wemos Mini, we have D1 for clock and D2 for data. If you're on an Arduino, those are A5 for clock and A4 for data. And if you're on any other kind of ESP32 board or something like that, what I recommend you do is refer to the data sheet for the particular device you're using. But other than that, the wiring is actually very straightforward. So here's the code that I got running on the Wemos D1 Mini, but as with the wiring that I showed you, I've tried to make this portable so you can use exactly the same code as written here on a ESP8266 chip or an ESP32 or any Arduino board as well, and you shouldn't need to make any further modifications to it. So I'll show you how I've been able to do that as we go through. So in the first section at the top, we've got this section of includes. So this is where we've got some external libraries that provide some sort of functionality that we want to bring in and use in our own code. And the first library we want to include is something that will let us access the Wi-Fi connection. So if you're using an ESP8266 board like the Wemos Mini,
the library you want to use for that is called ESP8266 Wi-Fi. If you're using an ESP32 board or an Arduino board, then that library is just called Wi-Fi instead. Other than the fact that the name is slightly different, these libraries are otherwise identical. They have exactly the same methods in them, they take the same parameters. So all we need to do at the top of the code is to actually include the correct library depending on the type of board we're targeting. And to do that, that's what these include preprocessor directives are doing here. So I was saying if defined ESP8266, and this is a flag that gets set depending on the board that you are targeting for your project. So here I'm targeting a board called Lowlin Wemos D1 R2 and Mini, and that is one of the types of ESP8266 boards. So as a result, this flag gets set to true, and this library is included in our code. If I were to change the board here, and let's say I was instead to include one of these Arduino boards at the top, well, Arduino is based on AVR architecture, so that means that this flag here would be true. Or let's say that we were targeting an ESP32 board instead. So if I scroll a little way down this list, you can see I've got a whole choice of ESP32 boards. And if I were to set any of those as the target, then this flag here would be true. So if either we're targeting the ESP32 or an Arduino board, we'll just include the regular Wi-Fi library. If we're targeting any of the flavors of ESP8266 board, instead we'll include the ESP8266 Wi-Fi library. And from that point onwards, we don't need to worry about that at all anymore. We can address the methods of those libraries in exactly the same way without worrying about which one we used. In the next section, we'll include a library called pub subclient. Now, I've used this in previous projects. This is a library written by a chap called Nick O'Leary, and it's a really, really great library for anything to do with MQTT. So MQTT is a messaging format, and that's how we're going to send the status updates from our cube back to a message server to say the current state of the cube, so what side is currently facing upwards. There's many different ways we could send that message. We could send it as an HTTP request, we could have a web server that someone accesses, but MQTT is really great for sending lightweight, simple messages such as sensor readings, and it runs on a very small footprint. It doesn't take much memory or processor intense or anything like that, so it's really good for sending messages between small devices like Arduinos and Wemos boards and things like that. So I've included a GitHub link here. You can also install it directly into your Arduino IDE if you're using it by going to Include Library, Manage Libraries, and then searching for pub subclient. And then you can see it here on the list here. And then the final library we're going to use is a library called wire.h. Now this is one of the included libraries that comes with the Arduino IDE, or the IDE for ESP8266 and 32 as well. And it's the generic library for creating any kind of I2C interface to different devices. So that's the interface we're going to use to communicate between the Wemos board and the sensor. Now, in some projects in the past, I've included a specific library used for accessing the sensor in question. So when I used an RFID sensor, for example, I included a library just for accessing RFID functions. Here, I'm not going to do that. Although there are some existing libraries for accessing the linear accelerometer that we're using, I thought it might be actually quite a useful exercise to show you how you can write functions directly against the I2C interface. So this could be really useful. For example, let's say you get hold of some sort of sensor that doesn't have a library pre-written to access it at all. So long as you've got the datasheet for the sensor in question, you can actually write your own functions against it to control it, to set values, to read sensor values as well. So I kind of thought that would be a useful exercise to show you how to do that. That's what we're going to be doing in this project. So I'm only including the generic I2C library itself. There's nothing specific here about the sensor board we're using. Okay, then we go on to the defines. So we're defining a single value here, and this is the I2C address of the MPU 6050 chip we're using. Now, just to explain here, the board itself I mentioned was called GY521. That's the name of the board, but the chip that we're actually going to address on that board, that's an MPU 6050. So that is the thing that has the I2C address assigned to it, and its default address is a hex value of 0x68. Now, if for whatever reason you've already got another device on your I2C network, no two devices can share the same address, but there is a way that you can assign it a different address instead. There's a pin on the board called 80, and if you write a high value to that, or if you simply connect it to the 3.3 volt line, the I2C address will be 0x69 instead. So if you've not done anything to your board, this will be the default address that is assigned to it. Then we go on to the constants. So the constants are variables that are not going to change throughout the duration of this project. And we start off with some settings to do with the Wi-Fi and the network connection. So this is the name of my wireless network that I'm going to join. This is the password which I'm going to use to access it. This is the IP address of the server on that network that is running my MQTT message broker. So you could be running Mosquito, for example. That's a very popular MQTT broker. Or in my case, I'm running Node-RED, which has a built-in ADES MQTT message broker as well. I'll explain more about that later. But this is essentially going to be the server to which we publish messages to say every time the cube is rotated. We're going to publish a message to this server to say what the current value is. This is the port on that server on which the MQTT broker is running. And then here we've got the topic that we're going to publish a message to. So the way that MQTT works is, rather than sending a message to a particular named device, you know, the way that you would write an email and you have to specify who it's going to, in MQTT what you do is you publish it to topics. And other clients can subscribe to messages that are published in those topics as well. And when a device publishes a message, it doesn't know if or how many subscribers there are going to be. Likewise, if you're a subscriber, you can subscribe to a topic that nobody may ever publish any information to. But other than that, this is kind of like a completely ad hoc way of structuring the way that you want to send data across your network, and that's you know, brilliant for escape rooms where you might have quite a different kind of setup. So the way I've structured this is I've got a parent level topic which I've just called dice, and then I've got a subtopic, and this device is going to publish to a subtopic simply called number 1 because this is going to be my first dice. If I were to have many dice, I would publish the next one into the topic dice subtopic 2, and then the topic dice in the subtopic 3, for example. So effectively I'm using the topic as a way of identifying which particular cube this message relates to. But you can use any you know, sort of topic structure you want to reflect the way that your props and the game flow in your room work. MQTT is a really flexible way of doing that. But this is how I typically kind of use it for my projects. And then finally we've got simply a kind of lookup array that's going to give us some convenient names to refer to the different ways up that the cube can be rotated. So we've got three axes. We've got the X, which is going left and right. We've got the Y going forwards and backwards, and we've got the Z, which is going up and down. And then these are the names corresponding to each of those sides being positive and negative as well. So we've got 6 possible sides. Then we go on to the globals section. So globals are variables that are shared between all of the functions in our code. I am going to create a new byte called side, and what you can think of this is like an index into this array up here. So side is going to take a value between 0 and 5, and that is going to relate to these 6 positions up here. I'm assigning it an initial value of 255 because when the code first starts up, we actually don't know which way the cube is pointing, not until we take our first measurement. So you can kind of think of 255 as being an unknown value. That's the way I'm using it in my code here. I'm creating another variable as well called the last raw side. That also gets initialized to 255. So to explain the way I'm using that, this is essentially like when you have a mechanical button. You know, when you press a button, you can find out that you kind of get erroneous bouncing, it's called mechanical bouncing, where you read it and it's high, then low and high and flickers a bit before it then settles on a constant reading. And we've got the same issue here. As players are rotating the cube around, if we were just updating our side value directly, as they twisted it around, you'd find it flickering between lots of different values very quickly, and that's not necessarily something what we really want to have. What we want to have is to wait until we get a steady reading that has been maintained for a certain amount of time to be sure that the dice has stopped rolling and it's definitely got this side facing up. And that's how we're going to use this idea of a raw reading, is what we are directly getting from the sensors at this point in time, but only when that has settled and consistently read the same value for a certain amount of time, that's when we're actually going to update our side value here. So that's the reason for that. Last change time, this is another thing that is going to be used in that debouncing process. So we're going to ensure that the amount of time that has elapsed since the last time a new value was read has exceeded some amount of time. So we're saying, okay, the dice has stayed the same way up for more than X amount of milliseconds. That means we're fairly happy that it's stopped rolling and we can update the side value. That's how that's going to get used. And then we create 2 global objects, one for the Wi-Fi client itself and then one for the MQTT client, and that's going to be based on the Wi-Fi client, and it's going to connect to the specified server and port which we included in the code up here. Okay, so now let's look at the setup function that runs when the code first starts up. And this setup function is a little bit more involved than the ones I've had in some of my projects, because we're going to actually write some configuration data to the accelerometer sensor. And I've kind of been quite explicit in the way I've shown how to do that, because I want to provide a demonstration of how to use that I2C interface. So we start off by just creating a serial connection, and we write the file name and the date at which this code was last compiled. This is purely for debugging purposes. And then we just write a little message to say what we're going to do next, and we're starting the I2C interface. So the first thing we need to do before we communicate with anything on an I2C network is to begin the interface. So we call wire.begin. And after do that, we'll just put a brief pause before we carry on. And then what we're going to do is we're going to say, okay, what device is it on the network that we want to talk to? And to specify that, we call the begin transmission function, and we pass in the address of the component that we want to talk to. So remember that every device on an I2C network must have a unique address. That is the way that it is identified on the network. And the address that we're passing in this case was the one that we defined at the top of the code here, 0x68, assuming that you're using the default value. and that is an address that is defined in hardware on the board. Every piece of hardware made by that manufacturer of that type will share exactly the same address, and that's a value that you'll be able to get from the documentation itself. So that's how we specify, okay, this is the component on the interface that I now want to talk to. And what we're going to do, before we go any further, we're going to effectively check that we've got hold of the device we were expecting to. So to do that, we're going to read the device ID that is reported back from this component. So how do we do that? Well, the device ID is held in a register address, so we need to read the value that's held in that address. And the way to do that is we actually, first of all, write the value of the address that contains the data we want to read. So here I've put a link to the board that we're reading. So if I load up that link, you can see here the page of documentation has got loads and loads of pages of all of the different registers that it contains in the addresses. But the one we're looking for is the one here on page 45. We can see something that says there's a register called Who Am I? And the address in hex is 0x75. And it says this register is used to verify the identity of the device. The default value is 0x68. So we're going to retrieve this value, and to do that we need to know what the address is. It's 0x75. So coming back to our code, what we do is, having opened a transmission to this device, we write 0x75, the address that contains the data we want to read, and then we end the transmission. Then what we do is we use the request from function, again of the same device, and we say what we want to retrieve. So we want to retrieve 1 byte of data from this device, and then after that we want to end the connection. So we began a transmission with this device. We we fed it the address of the register value that we wanted to read, and then we requested a 1 byte response to our request. And what we do is we read that response and we store it in a local variable called device ID. Now I'm storing that in a byte because a byte is all we requested. It's a 1 byte value here, and that was as specified in the documentation as well. And then, just to refer back to that one more time, it said that the default value of the register is 0x68. So what we should find, returning to our code, is that device ID now holds the value 0x68. And if that's the case, brilliant, we can send a message to our serial connection saying we were able to connect to the device. So we begun a transmission to the device at this address, we requested the value that was stored here, and then we received it, we read it, and it was equal to the value we were expecting. Brilliant. If any of those steps fail, we'll put out an error message instead that says couldn't connect to the device in question, and we'll just store an infinite loop here. Just one point of clarity, I've put MPU6050 here, which might have confused you, because in the wiring I mentioned earlier that I was using the GY521 board. So GY521 is the name of the board, and MPU6050 is the chip on that board that provides the accelerometer and gyro and temperature functions. Okay, so the data sheet I was looking at here, because we're talking about functions of the chip, relate to the MPU6050, whereas when I was looking at the schematics that showed things like the resistor values that were pulling up the SDA and SCL lines, they related to the GY521 because they're actually the additional components and hardware that's on the board rather than on the chip. So just to explain the difference in there in case that was confusing. Okay, so And this basic process here we're going to follow several times during the code here. So I sort of want to make that clear how this works. And you can use this for any I2C device. All follow the same basic process. You begin a transmission and pass in the address of the device you want to talk to. If you want to retrieve a value, what you do first is you write the address that contains the value you want to receive. You end the transmission. And then you receive the response to that request. You say how many bytes of data are going to be in that response, and you store that value in a variable using the wire.read command. And then once you've done that, you've got a variable here that you can treat just like any other variable in your code. So we're going to repeat that again, and this time we're going to do a little bit of configuration of the board. So remember I said that this board actually provides kind of multiple functionality. It doesn't just have a linear accelerometer. It actually also has gyros, and it has a temperature sensor. But we're not going to use them in this project. And because I mentioned earlier again about battery and power requirements, it's a good idea to kind of reduce the number of functions that are running that kind of we aren't really making use of. So what we're going to do is we're going to turn off the functions on the board that we're not using this project and only leaving on the accelerometer readings. The other thing we're going to do is we're actually going to reduce the resolution of those readings, because we don't need to be updating them 1,000 times a second for this project. You know, we can do it much slower, and that again is going to use less power. So to do that, I'm once again going to refer to the datasheet, and this time we're going to look at the registers which are mentioned on page 42. So here we've got a register at address 6B, and it's called Power Management 1. And this register here has individual bits that control various functions of the chip, as we can see in the description. It says the register allows the user to configure the power mode and clock source. It also provides a bit for resetting the device and a bit for disabling the temperature sensor. So we don't want to set the reset bit particularly. We don't want the board to be asleep either. What's this cycle bit here? Well, let's have a look on the description of the next page. It says, when the bit is set to 1 and sleep is disabled, the chip will cycle between sleep mode and waking up to take a single sample of data from active sensors at a rate determined by LP wake control, which is on the next register along. Well, that sounds perfect for what we want to do. We don't need to be constantly taking measurements. We're quite happy to let it go into a sleep mode, wake up every now and again, take a register, and then go back to sleep. So when this bit is set and sleep is disabled, so we want to set reset to 0 because we don't want the device to be reset. We want sleep set to 0 as well because we don't want the device to be asleep. We want cycle to be 1 because this is the cycling mode that we want to activate it. Temperature disabled. When set to 1, this bit disables the temperature. Yep, so that would be set to 1 as well because we don't need the temperature to be read each time. And then we have something called clock cell, 3-bit value, specifies the clock source. Let's go back to the previous page here. And the clock source says, upon power up, the clock source defaults to the internal oscillator. Well, that's fine for us. So the last 3 bits can all be set to a value of 0, which is using the internal 8 MHz oscillator. So back in our code, the set of 8 bits that we want to write to this register address here is a binary value that disables the sleep mode, disables the temperature sensor, puts it into cycle mode, and uses the default clock setting. This is the value of 0s and 1s that we want to write into this register address that correspond to each of these individual settings. And this is how we're going to do it. So writing a value to an address is kind of even simpler than the example we had at the top, because the example we wrote to an address to say what we wanted to read, and then we requested a result from it and read the result. Here what we're doing is we simply write the address we want to write to in one line, and then we write the new value we want that address to hold as a separate line. And that's it. And then we can end the transmission. Okay? In the next line, what we're going to do is we're going to do a little bit more configuration as well. So once again, we begin a new transmission. Each time we begin and end a transmission, every time we have a new value we want to set, we don't hold it open. It's cleaner just to do that. Every time you have a new registered address, you start a whole new transmission for it. And this time we're going to be addressing 0x6c. Now this is the very next register in the board. And you see the last one was called Power Management 1. If we look into the next register, we'll find that this is Power Management 2, unsurprisingly. And this holds some other configuration values for us. So what we have here is we have the frequency with which the board is going to wake up. We've set it into this cycle mode. So we've set cycle to 1, we've set sleep to 0, we've disabled the temperature. And now what we're going to see is how often do we want it to wake up and take a new reading. So that is in the first 2 bits. And then we also have the option to turn off the accelerometer and the gyro in 3 axes. So we're using the accelerometer. So we want to leave XA, YA and ZA enabled, but we don't need to use the gyroscope. So XG, YG and ZG can all be put into standby mode. So we've got the frequency of wake up, and then we can put the gyroscope into standby mode, but we want to leave the accelerometer waken up. So if we go back to our code again, what we end up this time is 0001111. That is for putting the gyros to sleep and waking up the accelerometer, and then we're setting a refresh rate of 0, 1. So that corresponds to a wake up frequency of 5 Hertz, and I think that will be absolutely plenty really to get a reliable rate with that. You can play around with different measures if you want, but I think for the kind of reliability and speed of response we need for this particular application, 5 Hertz is absolutely fine. And then again we end the transmission. So this is kind of if you haven't seen this before, this might be a little bit complicated, but it's actually not that difficult to get through. This is an example of reading a value here. So you specify the address you want to read, then you request the response and you read it in. And then we've got 2 examples here of writing new values. And same idea again, you first of all specify the address you want to write to, and then you write the new value there using write this time. So it's actually really powerful, and you can use this for any I2C sensor at all. If you've got the data sheet that you can refer to, you can write your own functions to read and write any values you want to the sensor. It's very powerful. Okay, phew. With that out of the way, we now get on to slightly more boring bits. So we now simply connect to the Wi-Fi network. If we're using the ESP8266, this has got a little function here that can act both as an access point and as a client connected to another Wi-Fi network. So effectively it can act as both a Wi-Fi server and a client. And in this case, we want it to be a client connecting to an existing network. So we just make sure that we have the Wi-Fi mode set correctly for that. After that, we begin the Wi-Fi network with the specified network name and password, and we enter a little loop that just waits until the Wi-Fi status is connected. When that's done, we will print to the serial monitor the IP address that we were assigned, and then we will also publish a message to the server to the MQTT server just to say that we have come online. Now we get onto our main program loop. So this is going to run just around and around forever while the code is active. So the first thing we do is we take a note of the value of millis. So this is an inbuilt value that tells us in milliseconds how long the code has been running for since startup. And then what we do is we need to retrieve from the sensor whatever the latest values are from the accelerometer. So hopefully by now this kind of format is looking a bit familiar to you. We begin a transmission with the I2C address of the accelerometer. And this time the register address that we're going to write is 0x3b. Again, if I just refer to the datasheet, you'll find that register 3b here is the address at which the accelerometer out values start. They then follow, we then have accelerometer X out, high and low, and then the Y, and then the Z. So we've actually got a total of 6 bytes of data that we want to read starting at 3B. So what we do is we'll write the value that we want to read from, we end the transmission, and then we use wire.requestFrom, just as we did to get the device ID, but this time we want to read 6 consecutive bytes from those 6 registers in a row. That's going to give us the X, Y, and Z accelerometer readings. Then what we do is we will read those readings. So the way that they are stored, the way that they're arranged in the register values here is that we have a high bit and a low bit for each value. So they're sort of high byte and a low byte. So they're 2 byte values for each axis, and we're going to read them into a 16-bit integer. So that's what we're doing here. We're going to take the high byte and shift it to the left 8 bits, and then we're going to read the low bit and put it on the right hand side with each of those. This is kind of, if this bitwise operation is unfamiliar to you, don't worry too much about this either. What this means essentially is that we are able to read a greater range of values than we would be able to if each axis were represented only by a single byte. That's what we're doing here. So we're getting a long value for each of our axis measurements, and the way we're doing that is by reading 2 bytes of data, but then we have to arrange them into a high and a low section, and sort of, you think of it a bit like concatenating them basically back together into a longer numeric value. And then what we need to do is we need to actually work out from those raw readings from the X, Y, and Z axis, we now need to work out which side is facing up. So remember, I mentioned right at the top of the code, we do this by kind of using a temporary variable, which we'll call raw side, and we'll calculate what the raw side that's pointing up right now is based on these sensor values. So if the absolute value of the acceleration in the x-axis is greater than the absolute acceleration in the y-axis, and also if the absolute acceleration in the x-axis is greater than the z-axis. So what this has told us is that the magnitude of the x-axis is the greatest of all 3 axes. And if that's the case and it is a positive positive value as well, then what that means is we're saying raw side is 0. So raw side was our index at the top here, and remember that 0 we said was right. So this corresponds to what I've written as x plus here. So the axis that is experiencing the greatest acceleration due to gravity is the x-axis, and it is experiencing it towards the positive direction. So we're saying that's right. Okay. Otherwise, if we get to this section here, the reading we're getting from the x-axis is still the greatest value, but now it is a negative reading, so it must be the other way up. So now we're saying that the cube must be oriented so the left side is up. Okay. Otherwise, we'll enter this section here. Now, this case is almost identical, except we're just looking at the different sides. So now we have the case that the y value is greater than x and the y value is greater than z. And if the y value, so this is the forwards and sort of backwards ends of the chip, if it is towards the positive end, that must be lying on the front side then. So we'll say raw side is 2, and if otherwise if the y value is negative, it means it must be lying on the back side, so raw side is 3. And we'll do that again with the z axis, and if z is the axis that has the greatest magnitude of the force of acceleration of gravity happening through it, then it's either the right way up or it is completely upside down. So those are our 6 possible ways. You'll notice that I've not actually assigned any threshold values here at all. I'm just looking at literally the axis that has got the greatest force applied through it. So if you imagine the cube kind of on a corner, on a 45-degree corner, technically it would simply say which face is most pointing up. It wouldn't have to exceed a particular flatness or anything else like that. And then what we'll say, okay, so this is populated value called raw side, and what we'll do is we'll compare that to, okay, well, what was the side that we thought was facing up based on the last set of raw readings? If it is different on this time through the loop than it was on the last time through the loop, then we'll update the value, and we'll also update the value of the last change time. So what this means is that the cube is still sort of wobbling around somewhat, and we've got a different reading than we did last time. So let's just keep track of, well, when was the last time that we recorded this value? Otherwise, if we've got the same result this time round as we did last time round, let's see how long ago it was that the last value was changed. So we'll do that by comparing the now value to the last changed value, and I've just hard-coded a value here of 200, so this is a fifth of a second. Now that's not completely coincidence value though, because remember that when we came up here and we set the configuration for the refresh rate of the sensors, this initial 0, 1 here set the refresh rate to 5 Hertz. So our sensor is reading 5 readings a second. It doesn't seem much point to have this being compared at any faster rate than that, because we know we won't have had any new readings from the sensor in that time anyway. But if the reading that we get on this time through, which is raw side, is the same as we got on the last time through, and that was at least 1 reading ago, so the time that has elapsed must be from the last frame of the reading, well, in that case we'll be happy to say that, okay, the cube has settled down, it's not wobbling about anymore, so we'll update the actual side that we've got. This is no longer the raw value. We will print the new side to the serial monitor connection, and finally we will actually publish a message to our MQTT server. We'll set the device ID, and we will set the new name of the side that we have turned to. And then this section here, this simply ensures that we are actually connected to the MQTT server. So rather than simply calling this once in setup, we'll place this in the loop, which just means that if for any reason we lose our connection to the MQTT server, this will kind of automatically reset it up again. So if the MQTT object does not report that it's connected, we will reconnect and we'll supply the device ID, and we'll just put a little message that says we've been connected okay. If for whatever reason we can't connect, we will put a little error message saying couldn't connect, and we'll dump the state. We'll wait 5 seconds before trying again, and we will simply keep on looping round this section here until we're able to reconnect again. The MQTT.loop function, this actually means process all the commands that have been queued up. So when we call the publish message up here, it doesn't actually publish the command straight away. What it does is it kind of adds that into a queue, and that queue of commands is actually delivered when we call the MQTT.loop function, which we do once at the bottom of every frame. And then finally we put a short delay in just to slow the code down slightly, and then we continue looping through it all over again. So here I've got the flow that's running on my Node-RED instance. So this is responsible both for retrieving the messages that the individual cubes all publish, for actually running the MQTT server that they're publishing to, and then for updating that visual display which I demonstrated in the video that shows the images of the different dice faces depending on which way up the cubes are turned. So I'm starting off, I'm actually running the MQTT broker from within Node-RED itself. In previous videos I used a broker called Mosca. That's actually now been discontinued, but there's a new broker called AEDs instead. If you don't have that node installed in your Node-RED instance, you can come to Manage Palette here and go to Install, and it's a node called Node-RED Contrib AEDs. And on the basis, I've used it not for very long so far, but it seems perfectly robust and reliable and things to me. And the great advantage of running it from within Node-RED itself is it means that it starts and stops when your flow stops. It makes your code much more self-contained as well. If you are running another MQTT server, so let's say that you are running Eclipse Mosquito or something like that already locally, that's fine. You can carry on using that, and you can simply point your devices to publish to that server instead. But if you're not familiar with MQTT, or if you're not familiar with Node-RED that much, I recommend using the built-in one like AEDs, like I am. That makes your code just a little bit easier to maintain, I think. So having defined that up here, the first thing I do, so I've got an inject node here, and this starts off once after the code has been running for a second. And what it does is it sets some initial global values. So I've got 3 global values. I've got one called dice1, dice2 and dice3. And you can see that they all get initialized to a value here called default.svg. So what this is a file name. You can see it's an SVG image file. And these variables here are going to be the 3 images which I'm going to display on my web page that shows the values of the 3 dice. Now if you're only using 1 dice, or if you've got a different number of dice, obviously you can have a different number of global variables accordingly. The reason I'm assigning a default value here, so this is actually a blank SVG file, it's just a white image basically, but it means that you don't get kind of a nasty broken image link when the web page first loads. So before we've actually received any updates from the device itself, we don't know which way the cube's up are facing, but we need to display something. So I've just put some blank images in those places instead. And these are saved in the static resources directory of my Node-RED instance. So I'm able to address them by just putting a leading stroke here and then the file name. So assuming you're on Windows as I am, this is the directory in which those files are saved. You can see I'm in my user folder, in my .node-red static directory, and this is the default image which I'm displaying here. And then I've also got the SVGs corresponding to each of the other faces as well, which we'll display later. Okay, and then having done that, the node here follows a link that actually goes to the section that updates the web page. But we're not going to look at that yet, because at the moment there's actually not very much to display on there. Like I say, this is the initial starting values, and until we get some sensor readings in, that's actually just going to be a blank page. So what we'll do is we'll look at the next section instead, and this is the flow that gets triggered when a new sensor reading is actually published by one of the cubes. So it starts with an MQTT in node, And what this does is this listens for any incoming messages that are published to any of the subtopics of dice. Now, if you remember from the Arduino or the ESP code, which I showed you a moment ago, the device ID and the topic which each of those devices published to was dice and then /1 for my first dice, or dice /2 for my second, and things like that. So the way that this is written here, this hash is like a wildcard that will listen for messages published by any devices in a subtopic of the dice main topic. Okay, so it's picked up a message that has been published there, and then we've got a function node. We'll say, okay, well, we'll take the payload of that message. So that means the value that was actually sent into that topic by one of the cubes. We'll put a leading stroke on the beginning, and then the contents of the message payload, and then a .svg extension on the end, and then we'll return that. So what this is doing effectively, if I can just refer back to my Arduino code briefly, remember that we had the side names here, right, left, back, front, top and bottom, and when it was detected that the side had been changed, what we published here in this line here was we published the device ID, so this is going to dice/1 if it's the first cube, or dice/2 or dice/3, and we published the side name of the index that we're currently looking at. So the value that comes in, the message.payload in that node red, is one of these values here. It's just the word right, left, back, front, top, bottom. And what we're going to do is we're going to put a leading stroke on the beginning of it, and then that payload, and then .svg on the end, to turn it into the files that we want to display on the web page here. Okay, that's what the function node does. And then we go into a switch node here. So remember that our MQTT in node here listened for all of the subtopics of the dice topic. So at this point we don't actually know which one of the dice was updated. We just simply know one of them was. So now what we'll do is we'll do a switch node, and we'll say, okay, well, which topic was it that had this message published into it? If it was the first topic, we'll send it to the first output. If it was dice/2, we'll send it to the second output, and if it was dice/3, we'll send it to the third output. So here we've got 1, 2 and 3, and what we'll do very simply here is if the message was received on the dice/1 channel, well, we'll update global.dice1 to the message.payload. If it was received in the dice/2 channel, well, in that case we're going to be updating the global.dice2 variable, and if it was received in dice/3, we'll update the global.dice3 value. And remember that the payload in all of these cases now has been updated by the function node here to include the leading stroke and the .svg. So what we now have is we've got global values called dice1, dice2 and dice3 that started off all being set to /default.svg, but now every time any of them have been modified by an incoming message that has triggered off this set of nodes here, what we've now got is the incoming payload that was something like top, front, left, right. We've added the extension, and then depending on which topic it was published in, we've updated those three values instead. So we've got three global values that should all have the latest information received for each of those sides. And then each of these goes to update the web page at the bottom, just as we did on the initial startup as well. Okay, so what happens here? Well, now having updated these global values in this section here, so we know that the global values are all up to date. What we now need to do is to kind of pass them along to the web page. Now I'm using a node called the UI Builder node, and that's not actually able to directly retrieve global values. All it can do is retrieve values in the message that was passed into it. So what we're going to do is we're going to have one more node, a change node before the UI builder, and we're going to retrieve the global dice1, dice2 and dice3 values, and we're going to set them to be the message dice1, dice2 and dice3 values. So what this means is in this line here going into the UI builder node, we've now got a message that is, contains as part of it the 3 global values, or the latest value of the 3 global values that have been being updated constantly by this section here. And then they go into the UI builder. Now again, the UI builder is not a built-in node. You'll need to install this through the palette. So you'll see in my palette here, I have got a Node-RED contrib UI builder, and you can install that by going to the install here. So UI builder basically means that you can write a little website that's going to take all these values that you've been retrieving from your different devices and manipulating all the rest of it. We're going to write a mini website that can have CSS, it can have an HTML file, and it can have a JavaScript file. And this is going to define how these values are going to appear on a website. So if we look at the HTML file to start with, if I just extend this slightly. So our HTML is pretty basic really. We're going to include the style sheet, the CSS file. We're going to create a div element which we're going to call app, and that's important because we're going to, anything that's going to be updated dynamically basically, we're going to contain all inside this one div, so we'll call it app. And our 3 dynamic values are just 3 image tags. So we've got image 1, image 2, image 3. Again, the source of them at the moment starts off as being default in every case. We'll change that in a minute. We'll give them an ID. And then we include our libraries that we're going to use here. You don't need to change any of this. So the only bit you really need to change is this section here to reflect whatever you want to have on the page. And it doesn't have to be images. You can have text. You could have a table, a graph, anything else you want to dynamically change based on values that are being passed in from your Node-RED flow. You just put here in this app section. And then if we go to the corresponding JavaScript, so this is using vue.js, which is a JavaScript library that makes it possible to kind of do dynamic updates. And we'll define an element based on that app which we had here. So this is our app div ID here, and we'll kind of link our view element to that. And then what we will do is we will have a function when the library is first loaded, so that's when this mounted function gets called. We'll start UI builder, we'll get a reference to the view app itself that we're referring to, and then we will set up a callback. So all of this, again, you don't need to worry about. This is all of the bits where kind of the magic happens, as it was. Remember I said that we were passing in a message through our node flow, and we had retrieved those 3 global values and we put them as values into the message. That's what we did here. We set message.dice1 to be the global dice1 value, we set message.dice2 to be the global dice2 value, and we set message.dice3 to be the global. And what we're going to do here in our JavaScript is to use those 3 values that were in the passed in message to set the source of the 3 image tags that are in our HTML file. So these 3 HTMLs, you see we've got refs here called image 1, image 2 and image 3. These refs are what we refer to here in our JavaScript. So we update the source of those 3 image tags to be equal to the value of the message dice1 and dice3, and they referred to our files that we had saved in our static directory that Node-RED can refer to. And after all of that, what that means is that this node will publish a website at the URL listed. So this URL is simply UI builder, but you could change that to whatever you want. So if we load a new tab and go to our local host with UI Builder on the end. Now at the moment obviously there isn't a whole lot to see here because I haven't had any updates from any of my devices. So the value of all three of my images is simply going to be that default SVG, which I told you was empty. So what I will do instead is I will simulate some alternative values instead. So let's say that we set the first dice to top, we'll set the second dice to left, and I don't know, let's set the final dice to bottom.svg. So these are simulating the payload that would have come in when the cube is rotated. It has the leading stroke and the SVG extension put on the end. But I'm going to put them here. Then what I'll do is I'll just deploy those changes and then trigger this node to set those values. And now when we look here, we'll see that we've got our three images that have been updated based on the values that we set here.
So that's it for my Smart Cube puzzle dice tutorial. I hope you found that kind of interesting and useful. And, you know, I can actually see this being the basis of many kinds of interesting escape room puzzles. Not necessarily dice-based, but any kind of portable object which players need to orient in a particular location or to rotate in a particular pattern. I think these could be useful. As always, I will put the code download, so both the code that's running on the ESP device and also the Node-RED flow and also the wiring diagrams and the parts I'm using and everything. I'll put those over on my Patreon page, which is linked in the description below. I'm only able to make these videos with the support of my amazing Patreon donors, so I do want to thank each and every one of them. Thank you all so much. If you would like to, and if you are able to support me, you can head over to my Patreon page where you'll find downloads of all of my previous projects on this channel, and that would be amazing. If you cannot, or if you don't want to, that's fine as well. I'll keep on putting videos in this channel anyway, and you can just follow along with them and copy them down as you go along. That's great. If you end up making a project inspired by or using any of this kind of technology, please let me know. I love to hear from people about the sort of projects that they're making, the ways that they're using this technology. That's what I love about doing this job, and that's the reason why I do it. So I always love to hear your comments. If you have any questions or anything wasn't clear in this video, do let me know that as well. Other than that, I will just say thank you all very much for watching, and I look forward to seeing you next time.